all of the organizers for having me here and giving me a chance to talk about some of our machine learning work. And yeah, about how we can use machine learning as a tool, particularly in theory, for a variety of applications. And though I'm going to show some fission applications, which of course is relevant to some astrophysical calculations, I'm going to try to give a bigger picture of just where in general can use machine learning across the board. And this is generally thinking about machine learning in a couple of different ways, particularly as fast emulators, either because our calculations are too slow and we want to speed them up, we want to do good uncertainty quantification, parameter estimation, machine learning for uncertainty quantification, whether it's just to use emulators in those ways, or even I'm going to talk a little bit about some probabilistic methods that we've been using to try to directly do uncertainty quantification without having to go through some parameter optimization or whatnot. And also as a way to supplement both experimental data where it's hard to measure, impossible to measure, or we just can't measure everything, or even as a way to supplement theory calculations. And so there are two things that I want to focus on. And the first one is this probabilistic machine learning algorithm that we've been working on, which is the mixture density network. And as I'm sure you're all aware that typical neural networks, the idea is that you have this non-linear function parameterization that is mapping an input to an output. And what we do with the mixture density network is that instead of directly mapping input to output, we're describing our output as a sum of Gaussians. And then we use the neural network to learn the means, the widths, and the weights of each of these Gaussian distributions. And this is very nice because it actually provides you a full posterior distribution for each of your predictions, instead of just where many methods give you just a mean value and a width. This actually provides the full distribution. Then the second thing I'm going to talk about is using Gaussian processes as emulators, which again has come up a lot in the field to this point. But the idea is generally that right with your model, you're describing some type of data that has an uncertainty on it, and you just replace your model with this Gaussian process emulator, which has some mean function, a kernel function, and it's just a distribution of functions that you're mapping, or you're figuring out a map between, again, input and output. And then this has also is used many places for fast emulators. And you can also use Gaussian processes to model the discrepancy between your model and data, where maybe there's a systematic shift, or in some regions of your model space, maybe there's physics missing that you don't quite get up to where the data should be. And a Gaussian process is also a nice tool to be able to model this discrepancy. And so we've been using particularly these mixture density networks as probabilistic machine learning techniques to propagate uncertainties. And so the first thing I want to show is just that they do propagate uncertainties faithfully, where we're using, again, these are fission mass yields, but you could imagine this on any type of observable that you're interested in, where we have some exact function shown in the black. We assume there's an uncertainty around it, so we sample this uncertainty and construct our training set of these samples around a mean value, put this into our mixture density network, turn the crank, and then see what the predicted uncertainty is. And what I'm showing here is that almost independent of the uncertainty that we put onto our sort of fake data, in this case, we get out almost that exact same uncertainty, whether we're looking at 5% uncertainty or 20% uncertainty. We get within 2% of the uncertainty that we put into our calculations. We have a little bit more trouble when we go down to, say, 1% uncertainty that we're assuming on our simulated data, but again, we're still within 10% of what we put in, and I think that's pretty good. And there are probably ways that could augment these types of neural networks that would, or even how you construct your training set that would make this even better. And so then, since we're able to get out well-quantified uncertainties, we wanted to look at this as a way to interpolate and perhaps even extrapolate beyond, could say this again is sort of mock data, but you could think of real data where you have measurements at specific energy points or specific nuclei, and you want to know what could be in between these points, and can I put uncertainties on that as well that come from the uncertainties of the surrounding points. So we looked at, again, fission mass yields, and our training set was at specific incident energies at thermal 1 and up to 4 MeV in 1 MeV integers, and then we made predictions between these training points. And so here's a prediction at 2.5 MeV, and then here's one close to 4 MeV, and you can see that in each case, the comparison between the exact calculation in black and the red calculation are almost on top of each other. And we have, hopefully you can see these orange densities are the uncertainties that came out of the prediction. We also looked at extrapolating beyond the training set, which of course is always a little hairier when you're talking about any type of machine learning method. But even looking at 5 MeV, which is beyond, or 4 MeV cutoff of the training, and at almost 9 MeV, we have, in some cases, pretty good agreement. In some cases, especially as we get farther away from our training set, we're doing a little bit worse. But again, these predictions come with uncertainties, and our uncertainties are getting larger the farther away from our training set that we get, which is, what you're looking for, because you would think that you would want a method where if your predictions are farther away, they're probably more uncertain because you have less of an anchor. And then I also mentioned that these probabilistic machine learning algorithms give you full posterior information. So in this case, we looked at 4 data sets, which are shown by these vertical dashed lines of the different colors, which all come with an uncertainty. And we constructed a training set that we drew from these uncertainties, which is shown here by the red line as our training set, because somehow my colors didn't all come through here, which I apologize. So then we constructed this training set, we put it through our machine learning algorithm to see then what it thought the sort of best value for this data should be. And that's shown by this black curve here, where you see that, again, this isn't just a weighted average of all of these data sets, but it actually inferred something about how well measured were these, which data sets are discrepant, and you can see it kind of comes out what we would hope. Right? It's bunched around the well measured sets that are closer together, and sort of has very little weight over this outlier. And then with my few minutes of remaining time, I want to talk about Gaussian processes quickly. And again, as I mentioned, a lot of groups have been using Gaussian processes as emulators for their models, especially to do uncertainty quantification in looking at large parameter space and to best fit observables. We're doing something similar where we're looking at, in particular, highly correlated parameter spaces, where we have potentially discrepant data, and we want to see if we can rule out any of this data. And so we're looking at here kinetic energies of fission fragments. You can see that there's a large spread in these 3 data sets, which we can parameterize and put through our models, but we want to see if particularly we can reproduce the average neutron multiplicity using each of these data sets and some other correlated parameters that are within the model. And each of these 3 plots on the right corresponds to one of these curves. You can see that there is some model parameter that we can adjust internally to reproduce the neutron multiplicity, even though there's a wide range of kinetic energies here. And so then we could propagate these parameters through our full model and see what else we get out, and have a better idea of which of these data sets could potentially be excluded and is not as physical, because measurements are hard. And then finally, talk about using Gaussian processes to model discrepancy as well. In our models, we have particularly some trouble modeling the average neutron energies that come out of the fission fragments. As you can see here, the difference between our model calculations are the red stars compared to experimental data, which is these black lines. And of course, there are uncertainty bands around the blue, but it, for some reason, did not come through here. But we had a summer project that was looking at using a Gaussian process to model this discrepancy. And you can see, at least from these means, the blue, which is the Gaussian process, that regardless of how different the discrepancy is between uranium and plutonium, the Gaussian process can model the discrepancy in both cases. And so again, this is another place that we have models that do not necessarily match data in all places, and we just need to correct in some regions. And so for the fear of going over time, I'll just leave you with my last slide, and I'm happy to take any questions or to elaborate further.